so now we're in chapter 6, and I like this chapter because, chapter 1 through 5 is chemistry. We laid a lot of the groundwork. Now we hopefully have a better understanding of how the periodic table is set up. But I think I really like chapter 6 because I feel like we're really launching into the real deal of how chemistry works and the different bonds that are formed between atoms. We're going to talk today about the ionic and covalent bonds, which you've probably heard of before in at least one science class in the past. And we sort of like to put these bonds into categories, ionic and covalent. But just realize there is a little bit of gray area there as far as something being fully ionic or fully covalent. There's not really a pure one type or the other. So we're going to learn how, in this first section, just to classify those bonds based on their electronegativity. So the first thing I want to talk about is what even is a chemical bond. And all that is a force of attraction that holds two atoms together. So I might liken this to, if you've ever held two magnets together with their poles opposite, you feel that little pull. Even on my Earth toy over there on the table, you feel that magnetic pull between the magnets, and that's when we see this high potential energy. You feel that energy, but then once you let them snap together, that potential energy goes way down. You don't feel that pull anymore. You've just got a couple magnets stuck together. So that's really, in chemistry, our answer to a lot of things about why does this happen. Honestly, right there, it's because it's at a lower energy state. So if you ever, you're lost for an explanation on why something happens in chemistry, you might as well just try to say it's because it's at a lower energy state. And chances are you might get it right, because that's why things bond. That's why reactions happen. That's why all sorts of things happen in chemistry, because the material in the universe prefers to be at a lower potential energy. So another way you might look at this is a spring. If I'm stretching a spring out really far, it's going to pull back towards its original position. And then if I go beyond its original position, like over here to the right, I'm pushing the spring in too far, and now that potential energy goes back up, and it wants to go back out. So we get this nice kind of Goldilocks position, and just right in the middle is where that bond is going to happen. So that's what a bond is basically we're at a lower energy state if we're together than we are apart. Sort of like when you're bonded in matrimony, right? You're at a happier state when you're together than when you're apart. So nice love stories in chemistry. So first, the type of bonding we're going to talk about is ionic bonding. And that's going to be where essentially a deal is made or an exchange is made. If you remember back to last chapter, we talked over in group 1, the alkali metals, they are really eager to give up an electron, whereas the halogens are really eager to gain an electron. So we've got on the left, we've got sodium, who really wants to give an electron up, chlorine, who really wants to give to take in an electron because it will have a full outer shell and be like argon. Sodium, if it lost its electron, would go back to having an electron configuration like neon. So there seems like there's going to be a deal made here. And essentially there is. The chlorine sees that electron that sodium wants to give away and latches onto it, takes it into its outer shell. And now you have that bond between the sodium and the chlorine where sodium has essentially given up its electron and chlorine has gained it. So sodium would become a positive ion, giving up its electron. Chlorine becomes a negative ion, an anion, taking in the electron and you have what's called an ionic bond. I just want to be clear, obviously these atoms are not human-like. I sometimes give them human-like characteristics, like I'll say they're happy or they want something, but just remember, it's really that it loses energy. It's at a lower energy state is why this is happening. It's just easier for me to explain if I can give them a little bit of a personality, I guess. But the other type of bond would be a covalent bond. This is where the two atoms share their electrons. So we have hydrogen, which would like to gain an electron to be like helium. So if a hydrogen meets another hydrogen, they both would like to gain an electron. They say, why don't we share an electron in our outer shell? Then we'll both have 2 electrons in our outer shell. We'll both have the electron configuration of helium. And that is what's done. It's not one hydrogen taking the electron from another, like the ionic bond, but this time they're sharing the electrons. Same with water. The water, oxygen wants to gain 2 electrons to be like neon, have an electron configuration as neon. Hydrogen, again, would like to gain that 1 to be like helium, so they make a deal. They share those electrons so that oxygen can feel like it has 8 electrons in its outer shell, and then each hydrogen can feel like it has 2 electrons in its outer shell. And they all get along happily in that covalent bond. So hopefully you see the difference between ionic and covalent, where ionic is more kind of a give and take relationship, whereas covalent is more of a sharing relationship. And there's not really one clear type or the other all the time. So what we're going to do is we're going to classify them based on electronegativity. You can see rather than solid colors, we see a gradient going from covalent into ionic. How do we determine that? We look at the electronegativity of each atom in the bond, and we see how different those electronegativities are. If the electronegativities are very different, like they will be for sodium and chlorine, you're going to see a more ionic bond. If the electronegativities are almost the same, like you see with hydrogens bonded together or oxygens bonded to each other, you're going to see a nonpolar covalent, where, especially if they're identical, they have electronegativity difference of 0, it's going to be covalent and nonpolar. Now in the middle, you have what's called polar covalent, where it's kind of getting towards ionic, but not quite. Water is going to fall in that polar covalent category. If we look at the bonds between hydrogen and oxygen, we're going to find that they have an electronegativity difference between 0.3 and 1.7. So we're just going to look at a sample problem, and then we're done. A quick first lesson today. Looking at the electronegativity values, we're going to look at p-table. But we're going to compare sulfur and hydrogen, sulfur and cesium, and sulfur and chlorine. So the electronegativities, I'm going to list those out to the side here. Sulfur let's go to electronegativity. Sulfur has an electronegativity of 2.58. And then, what were the other elements? I already forgot. Hydrogen has an electronegativity of 2.20. Cesium has an electronegativity of 0.79, and then chlorine has an electronegativity of 3.16. So I'm going to write those all out so we have them in front of us. I already forgot. I know hydrogen was 2.20, cesium was 0.79, chlorine was 3.16. Do you remember what I said for sulfur? Was it 3.59? I'll have to look again. And now my PowerPoint's going to close out on me. To be expected to write those all out again. $2.58. Through 3.59 would be rather high. So let's see here. So again, electronegativity at 2.58 for each sulfur that was bonded with a hydrogen, which had an electronegative 220, cesium and chlorine, which were 0.79 and 3.16. So we can actually subtract those values to figure out the difference in electronegativity. And really all that matters is the positive difference. So I'm just going to take the absolute value of those. 2.58 minus 2.20 is 0.38. So you can see that's going to be right around here in that between nonpolar and polar covalent. We can be certain that that is going to be a covalent bond. Anything below 1.7 difference between the two electronegativities, we're looking at a covalent bond. Cesium and sulfur, we've got 2.58 minus 0.79, so that's going to be something like 1.78, 1.79. So 1.79, just above the cutoff for what we would consider to be an ionic bond. So you see how sulfur and cesium are going to be an ionic bond. And then 2.58 minus 3.16 is negative 0.58. Because I don't really care if it's positive or negative, I'm just looking for the difference. All right, 0.58, which again is going to lie somewhere in here in this polar covalent range. So you see we've got an example of two covalent bonds with the sulfur and hydrogen, as well as the sulfur and the chlorine. And then we have an ionic bond with the sulfur and the cesium. So in this case, by the way, I got ahead of myself here. I didn't really answer the question they were asking. They're asking which atom will be more negative. Looking at the electronegativity, remember electronegativity is the ability to attract electrons. So between sulfur and hydrogen, who do you think is going to take the electrons more? Yeah, sulfur is going to take them here. And then between sulfur and cesium, yeah, sulfur is going to take the electrons. And then, chlorine is going to take the electrons in that one. Yeah, I get it. So the electrons are going to go more towards the electronegative one. In the case of this one here, essentially sulfur is taking the electron. In both of these two, we would consider them to be sharing the electrons. So, any questions on today's lesson? We'll pick it up there.